Okay, I'm going to talk about projectiles for a little bit, and specifically in the context of the basketball video analysis that you did. So when we look at a projectile, you see that we have this kind of parabolic arc. This is a projectile launched like from the ground up and over, and it follows that sort of path. And the complicated thing about this when you first look at it is that at each time interval, and we'll pretend that each drawing of the ball here is, let's just keep it simple, is 1 second after the previous one. So at each time interval, you see that the actual velocity of this thing has changed, that it's a different direction, it's a different magnitude, it's not moving as fast as it gets higher, and then it's speeding back up as it goes down. So there's a sort of complicated nature to the movement of this. What's going to be helpful is that we're going to break this down into x and y components, because we have kinematic equations, the x monster, Vatvo, and the timeless equation that can help us to understand how things accelerate and move in a single direction. And it turns out that a projectile is really just something that's moving in two directions kind of at the same time. And to us, we just look at it and we just say, well, it's moving diagonally. But really, it's traversing a horizontal space and a vertical space, and it just happens to be doing that at the same time. So we're going to start by flattening this out. And so I take this and I scrunch it down, and what you see is right away, each of these time intervals seems to be pretty evenly spaced. And that's because in this experiment, and in general for right now with physics, we're sort of pretending we exist in a world where there's just no air resistance. So there really shouldn't be anything that's going to slow down or speed up the ball in the horizontal direction. Realistically, we know that as the ball pushes through the air, that air is going to be applying an equal and opposite force, and that should slow down the ball a little bit. And depending on how careful you were with your clicks on the basketball assignment, you may have actually pulled out a meaningful deceleration of the ball, or a negative x acceleration of the ball as it moved forward. But for our purposes right now, just to sort of simplify things, we're going to say that there is no x acceleration. Therefore, it shouldn't be surprising that when we look at the velocity of this, and I just made up this velocity for this example, but the velocity remains the same. And in fact, when we look at our Vatvo equation, we can simplify it and get rid of that acceleration, because acceleration in the x direction is 0. So that component goes away, and what we find is that, well, the final velocity equals the initial velocity in the x direction. Similarly, when we look at displacement, or the distance that the ball has traveled horizontally, we find in this case, because it's traveling at a constant velocity, it's a constant increase in the distance. And therefore, when we look at the x monster, we can also simplify that, since again, we know the acceleration is 0 in the x direction, so we can take out this component. We know we started at a displacement of 0, and so we can simplify our displacement as well, down to simply that the x displacement is equal to the x velocity times time. We had a constant x velocity, so if we know how long the ball's been traveling through the air, we can find out what its range is or how far it's traveled. With the vertical, it's a little bit of a different story, because we know we do have an acceleration in the vertical, and that acceleration is thanks to gravity. Gravity, negative 9.8 meters per second squared in the downward direction. And so what happens is, in this case, we're going to get rid of those lines, and we're going to scrunch this thing back together. And so it starts at the ground, and we're going to make up a number, 29.4 meters per second. I just picked that because it makes the math work out nice. 1 second later, that velocity will have decreased by 19.6, or I'm sorry, will have decreased by 9.8, because that's what the acceleration is. It's how much the velocity changes per second. So it has decreased by 9.8 to 19.6. 1 second later, it decreased by another 9.8, and then it decreased by another 9.8, and now at 3 seconds, the ball is here at the top of the arc. At this point, that's notable because that's the maximum height that it reached, and maybe that's an interesting thing to us as we're solving a projectile problem. But also at this point, it's when the ball is just momentarily hovering in regards to the vertical movement, and it's about to start coming back down. And so at this point, we see that negative acceleration continues, and therefore once it reached 0, now it just starts moving in the negative direction with a negative velocity, and therefore returning back towards where it started. So 1 second later, it now has a negative 9.8 meter per second velocity, then a negative 19.6, and then a negative 29.4. And once again, we can use the same kinematic equations that we've been using previously to solve for what the velocity or the displacement is at any point in time, because we know the negative 9.8 acceleration. Presumably we were given, or we've already solved for the y velocity, and then we just plug in whatever interval of time you want. So if you wanted to know, at 2 seconds, how fast is it moving, or what is its position in the y direction, then you simply go to these equations and you plug those values in. When we put these two things together, here's the x and here's the y, we start to get a better appreciation for sort of where that diagonal came from. These diagonal arrows here representing the actual overall velocity are the vector sum of the y vertical velocity and the x horizontal velocity. And in fact, if you took this y velocity and slid it over here, you could sort of see that triangle that you're looking for. And so we're going to see a return of the SOHCAHTOA method to solving these types of things. We're going to solve for different components. Maybe you're given an overall velocity, it's 40 meters per second, 20 degrees above horizontal, and then you have to use that hypotenuse in order to solve for the x and the y components. None of that will be really novel things. It's just going back to some of the methods we've previously used in order to now look at something that's meaningfully moving in two directions at once, horizontally and vertically. And once we break that down, and once you get some practice with it, it actually becomes a pretty simple mathematical thing to solve. But of course, I want you to also, in the back of your minds, be thinking about, well, what's actually going on here? That really does help to break it into the two pieces. From an x perspective, things are pretty much just cruising, stay in the same velocity throughout the entire duration of the motion. And from the y direction, it's also pretty simple. Even though we've got these up arrows and then no arrow and then these down arrows, really you're looking at this constant negative 9.8 acceleration. And so while you start with this really positive velocity, it just decreases throughout the motion of this, going from some positive number to 0 here at the peak, and then continuing to some negative number before it gets back down to the ground. And one last notable thing about a projectile like this, if it started and stopped at the same point, so if let's say this is launched from the ground or from your hands, you launch something up, and then maybe another person catches it or it lands on the ground. If you start and stop at the same height, then what we find is that the y velocity, that vertical velocity, is going to be the same magnitude at the beginning and the end. Because for the first half of this, it was losing that magnitude, going to 0 when it reached the peak, and then for the second half of it, it regained that magnitude, which is part of the reason why when you throw something up, you don't want it to fall back and hit you on the head. It's going to be going about as fast as you launched it, again, assuming no air resistance. Also a good reason why you wouldn't take like a bow and arrow and just shoot it straight up. Seems like a fun idea, would be really bad from a physics standpoint. So there you go, a little bit about projectiles. Hopefully that helps in conjunction with the basketball activity that we did, and we'll start trying different examples of projectiles. Thanks.